let's hope that this is working for them, and we will start on class. This is should be the third lecture. Let me see, let me call up Moodle. Okay, now some of you have started doing the homework, right? How are you finding that? Is that okay? I'm sorry, some of you are starting to mess around with it. Something like that. I think it's next week, yeah. Okay, here's one of them. I guess I could click on it. Does anybody that has done this one, is their score low or bad enough that you don't want anybody to see it? No. All right. Okay. So I come in here and I can, if I want to, look at the results, see who's been working on it. Okay. If you guys say like, hey, I think I got this one right, I can go look at it and I can decide it's right or if it's wrong. This is going to take, it's going to take the average of those, okay? For when it's two people or two tests, it's going to take the average. If you really didn't know that, send me an email and say, hey, I really didn't know that. Could you get rid of that first one? And I'll do that for a little. Say what? It took a while. That one just turned it on and then never went back. It took them 2 days. 2 days. It's going to take you at least 2 hours. Anyway, remember, these are about a point apiece. When it comes right down to it, by the end of the semester, it's about a point apiece. I would get ahead of these as you can to get them out of the way. If you need to, go out to my website, like I've been saying probably 5 billion times, and you're bored with that by now. If you can't remember my website, just click here. This takes you right to the digital, and come down here, and this is some of that stuff that's out there. Now, some of them I ask you to please use a standard resistor size that's closest to, like for the ones for figuring out a resistor size, use the one that's the closest you could get to it. So for that, go out here and look at standard resistor and capacitor values. So, because I don't expect you to know that, so you can come up here and look at those. If you can't remember some of this stuff, like signed number conversions, if you haven't done that in a while, that can be a little difficult. So go ahead and look them up. These, I don't care if they're open while you're doing it. These are not tests, even though it says they're called quizzes here. When you go in there, I think it calls it a quiz, doesn't it? It is not a quiz. It is a somewhere in here it says a quiz. Anyway, it is not a quiz. It is just some homework. It's just that's what Moodle calls us. Okay. Now, we've done this. This is the one we should be on. I'm going to go through this one pretty quick and then try to get down to this one and see if we can make it today. I'm hoping that that this is picking up real good for my DE students. Okay, and I did find out, you would not believe what it was the other day. Remember the light switch or that went out? There's a button that says mute video. I accidentally hit mute video while I was doing all this stuff. So that's all that happened. I'm still hoping this is going to pick up. Okay, we started this one, didn't we? Barely. Uh, Somebody's playing some kind of music. I can kind of hear it. Uh, First of all, in doing any kind of digital design, you got to really clearly define what the problem is. Most of you know that, but it's real easy to make one little mistake or go, oh, well, I didn't know that or something. So try to define your problem as clearly as you can. This one, I don't know how many times you're going to hear me say this while you're at UNCC, but I'm going to tell you again and again and again, break the problem into smaller problems. Okay? I forget who told me this, but somebody, a former student, recently emailed me on that and said, if there was one thing that he's been gone for a little while. If there's one thing I want you to remember to tell your students, it's that. Break the problem down into smaller problems. Because if you look at a real big problem, or any kind of a problem like this that you got to fix or work on, most of the time they look too big and they can be overwhelming. Okay? Like looking at a degree, it's like, oh my God, I got to do all this. If you tried to look at all the tests and all the homework and everything you had to do and read all the course descriptions, you'd get overwhelmed and say, I can't do that. But if you could then break it down into the courses that you take and then look at just the ones that you're working on now that you have the prereqs for, and uh, look at topic by topic, and it's like, well, I can do this topic and I can do that one after I do this one. So if you break it all down into um, what the hell are you doing here? I think you're in the wrong class, aren't you? Okay. He does everything late. Come to class late. Yeah. Anyhow, okay, so that at least one person out there, I know it's more than one, said that this was the most important thing I taught them out of everything. Break it into smaller pieces. Uh, it's your buddy. Okay. Then we got to kind of develop some kind of a strategy. If you need a digital system, some of them aren't going to need a digital system. We are going to then proceed to some kind of detailed, systematic approach. You might be working on HDL. You may end up doing, it depends on what it's doing. You might set up that set of Boolean equations to fix a problem. I don't know. In the not too recent past, and I mean back when I was learning this stuff for the first time, we didn't have. I even remember when the first IBM PC came into our lab. We had three of them. I think we had a couple of Apple IIs, and I had a Commodore 64 because I was a poor little teacher and I couldn't afford anything more than that. But there were just a few computers around. We didn't have the kind of software that was out there that would do uh, this kind of design stuff for us. So what we had to do was set up the Boolean expressions and then try to figure it out and uh, sketch the circuit. If we could, we would try to simplify that in some way. Okay. And then we would draw the circuit by hand using some kind of a template, try to figure out what we needed. Everything we did was by hand on a piece of paper. And then they started coming out with some CAD software. When they came out with PSpice, oh my goodness, that was great. Problem with PSpice was we had to define, we didn't have the graphic software at that time. We had to define the circuits. So we had to do something like node 1 and tell it that it was connected to the positive side of a 5-volt source. And node 1 also was connected to, most of them were analog circuits at that time. We didn't have digital for this. So we would say it was connected to pin 1 of this resistor, and then have to tell it what resistor value it was, like 1K or 2K or whatever it was. On the other side of that, power supply, node 2 or node 0, whatever you wanted to call it, was connected to ground. So you had to describe this whole circuit in words and then tell it how you wanted it to run through some tests, and you would get the tests all written back on, on some kind of printout, and it would take a while to figure it out, but it was a whole lot better than the alternative. Okay, so that's in the not too recent past. If you did this, you would then have to put your circuit together. What could you do? You had to put it together. You had to put it together on one of those digital designers. And because we couldn't just, not even with PSpice, we weren't running digital type of circuits out there. So we had to put it together and then test it. Now, when we tested it, probably wouldn't work. Right? More than likely it's not going to work. Now we had to figure out, was the problem in the way we hooked it up? Was the problem in the DigiDesigner, or was the problem in our design? And there's probably several other. Is the power supply working right? Is my meter working properly? Several different things. So there's so many different places where something would go wrong. It depended on how complicated the circuit was, but sometimes we would use wire wrapping. Have you guys done any wire wrapping? Have you ever even heard of this? On some of the old IBM type mainframes that were out there, and this is true, they put all their boards in using wire wrap. And wire wrap, the pins were usually fairly long. They were very sharp, square pins. And when you put the wire on it, there was a little tool that the wire would come through. I wish I had a drawing of it. I can't draw it on there because all the DE class is getting, if they're getting anything, is the PowerPoint. So anyway, lucky them. They don't have to look at me. But this little tool, and it was just a little bit big enough to go over that square pin, and a wire would come through there, and then you had to press it down. Now this was really tricky because you had to press it with enough force that you're wrapping coils around that post, or that pin would stay right next to each other, because you didn't want them all stretched out. It would take up too much room on the post. You didn't want to push too hard, because then it would have them kind of all bunched up over each other, and that wasn't right either. So you had to learn to put just enough force on here to make it look real nice and neat. And you had to cut the wire to the point where it would only have like 3 or 4 wraps, because you didn't want to be able to pull it off. Okay, so we'd put on the wire wrap, and the nice thing about that is it was pretty stable. It was pretty permanent, but if it didn't work, this tool would also let you go right in there and back it off and take the wire right off. Biggest thing that happened on that, so you put on one side of the board, you put the chip in, and then you turn the board over, and that's where the pins were for the wire wrap. The biggest mistake there made was people forgot that you were flipping it over and the pin numbers changed. Okay, so a lot of them hooked those up backwards as far as the pin numbers were. Uh, Now, IBM and these guys that built these big mainframes would do this, and this would allow them to easily upgrade or easily make modifications to their system. And some of these things, to get some voltages in there, they actually had some tubes in there instead of little digital circuits. We had tubes. Now, you've never used tubes either, have you? Some of you have if you're musicians, because some of the better amps that are out there have tubes, right? You get a cleaner sound, and I think you can get a higher level, can't you? Or anyway, mine would be a real small little digital thing. But one of the things about a tube is they had a little heater underneath the plate. It kind of worked like a transistor, but it was meant, or it was working off voltages instead of currents. And there would be this little heat that would heat the plate, and that would let the electrons easily move off that plate and go across the or make that jump that they had to make. Anyhow, little bug would get in there, little roach, yuck, moth, something like that would get in there and get between that plate and the heater, and when they turned it on, zap. But now you got something that's keeping it from heating that up. So guess what? You had a bug in the machine. That's where the term bugs came from. So they, anyhow, we'll go on with some of this. Once you built all this and you figured out where your problem was, and you'd test all this out and you'd figure it out, and it took a while and it was exhaustive, and it could take hours and hours and days to complete. You really wouldn't be able to test it thoroughly. You would have to use a representative sample, because if you tried to test too much, there's just no way you could do it. Nowadays you could. You'd run PSpice and say, here, test it all. Test every possibility. Okay. Rarely did the circuit pass the first couple of tests, so you had to troubleshoot. So there's many places in which those errors could occur, like I said before, in the design, in the IC, in the connections, in the timing. Boy, in the timing, talk about one that's difficult to find. In the timing, in the fan out. There was just a lot of possible places where there was problems. So you get back to the drawing board, and that was literally, and begin redesigning and working and see if you could fix this problem. Okay, so when it finally passed, and we said it was complete, then we would go to a PCB, a printed circuit board, and put it on there. Now, a lot of these, this is before they even came up with the multi-layered boards. We were making our own PCBs, and we had to do those not the way we've got that one setup up in the lab. Have you all seen that one setup that Dr. Brown works with sometimes? We didn't have something like that. We actually had the board that had the copper on it, and you would lay out by hand little strips, and it was almost like developing a photograph. You would put this on there, and that's where all your wires were. Again, you had to make sure, were you upside down or were you right side up, and then put it under a light for a little while, and it would start that process. Then you put it in a solution that would etch off everything that wasn't supposed to be a wire trace on there. So we'd make those. Imagine how many problems we could have with those, right? You could have it backwards, or as you were etching some of this off, the the trace would break. So now you had to put a wire in place of it, and it just looked kind of trashy. So we had stuff, and again, you had a lot of testing to do. Is it a short circuit? Is it an open circuit? Is it a faulty IC? Did you mess up the trace? So on and so forth. And I'm talking about not too recent past. This is not that many years ago that I was doing this. And boy, am I glad. So when I see something like Xilinx or Multisim or PSpice, I'm going, great. And you guys are like going, oh, we gotta do we gotta do PSpice, we gotta do Multisim. It's like, well, do you want to do this? That's your alternative, right? And this was not much fun. It kept you busy, and that's why engineers made good money. Uh, so I did put there, like, you guys might be thinking it's ancient history. Uh, some of this was happening before I was born, but a lot of this was happening back, and this was some of the things I was doing. Uh, as late as the mid 80s, still stuff was going on. Well, when did the first PC come out? With the monochrome screen that was green. I remember you were really cool if you had the amber screens. Have you ever seen an amber screen? It's still the two colors, but it was kind of that yellow orange instead of green. And the amber was nice because it wouldn't burn out your, or at least I said, it wouldn't burn out your screen so bad. People would sit up, have uh, a spreadsheet up all day because that's what they worked on all day, and then when you turn the machine off, you could still see, like the X and Y axis for this little thing. But if you use an amber screen, that wouldn't happen. So the first PCs were coming out in '81, and it's like 1981, and here we are. It's like computers have always been here for you guys, right? There's always been computers. For most of you, not all of you maybe, but most of you, there's always been computers around. For me, I remember them bringing that first one in, and I remember making the joke of having to put on a seatbelt because this thing was going to fly. And when we got in that seat, we wanted to make sure we didn't fall off because it was moving so fast. Guess what the speed of that first one was? It's like 4.77 megahertz was how fast that processor was running. If we were lucky, it had a hard drive. If we were lucky. If we were lucky and had the hard drive, it was 10 megabytes. And it was the 5 1/4 size, 10 megabytes. And anytime you wanted to run a new program, we didn't have Windows. We'd put in a disk, a floppy disk. They were even too big for my pocket. I had to carry the boxes around. Gosh, it was awful. And you put it in there, and you had to know the name of it, and you had to know what drive it was on, and you had to type it in, and then it would run this program, and it would be I forget. I do know the word, but I've not thought of it all day. Real procedural type program where one step sequential type circuit or program. You'd have to wait and have the user type in information. If they typed in the wrong information, you just escape, get out of it, start over again. So, so the PCs were there. They didn't have too much graphics, so it wasn't that good. Well, I remember writing up a program that had resistors and capacitors, and it looked really crappy, But our resistors had the forward and backward slashes, so they were really crappy. But it worked. Okay, so everything starts changing. We step back a little bit. And 1970, this group of engineers gets started, and they were at Berkeley, and they've got this Don Pedersen, is it, I guess, and Ron Rohr began working on their first program called Cancer.
Wow, that's messed up.
Isn't it? Computer analysis of nonlinear circuits excluding radiation. They had to really work. They had to really work at that one to get the acronym right.
That made it even worse.
I know.
So basically, they really wanted to be able to come into a room and say, "Hey guys, I've got cancer."
Exactly. Exactly. It was like a guy I knew a long time ago. He was kind of weird. He'll never hear this, I'm sure. But he named his little band Passing Gas. So they could get up on stage and go, "Hey, we're passing gas." Like, that wasn't all that funny, and please stay away, or I'm moving toward the back now. But same kind of thing, right? Anyhow, that program, Cancer, eventually was called SPICE. Not P-Spice, but SPICE, Simulation Program with Integrated Circuit Emphasis. So that's back in 1970. By the 80s, the first commercial versions of SPICE were released for the PC by a company called Microsim. Now it's owned by Cadence, okay, and it's called P-Spice. All right, so we're lucky to have it. You guys fussed last week in the lab about having to use P-Spice, but I know it's a little bit harder to use because you haven't had to use it before, but it's a lot more powerful than Multisim. And guess what? When you use Multisim, guess what's running in the background to give you the answers? P-Spice. Okay? So, big changes started with Spice and P-Spice and the PCs, and now we're even getting PCs in the home and the office and universities. I remember there was a time when both IBM and Apple would be bringing computers to your school and giving them to you. Here, you can have them. And the whole reason for that was if I trained all you guys on a PC, guess what you'd probably buy when you went out to work? You'd probably buy a PC, right? What you probably bought for home was a PC. But if you're used to Apple's, you'd probably go that route. So, anyhow, we started doing this. Now remember, everything's sequential programming. There's no such thing as object-oriented, which meant like a Windows type machine. And by the way, are any of you real Apple gurus or real Microsim gurus? Like you, that's just the greatest thing in the world, and you'd have a fit if somebody said something bad about either one.
I hate Apple. Genuinely.
Apples are okay. Apples have some difficulties. They don't let you get in there and everything has to be made by Apple, and you can't get in there and do anything with them, right? But they're good. They are good machines. They typically don't have as many problems as typical PCs. The PC guys out there, IBM, I think they made a smart move by opening up the design so people could get the schematics and see what was going on. Some of this stuff, they wouldn't let you see what was going on, like on the microprocessor itself. You wouldn't necessarily see that. So you had to do some reverse engineering. It's not that hard. It's like, for given this set of inputs, this is what the output needs to be. So that's just a digital circuit. You guys could figure that out. So anyhow, so the PCs became a little bit more popular, and then, but again, we're still talking sequential programming. Apple came out with the wonderful Macintosh, and everybody's like, Macintosh, it's a type of Apple, right? It's just a type of Apple. But they had the first object-oriented type computer system. And that was allowing for them to click on icons to call up a program, and then it was the first object-oriented type of stuff going on. And Microsoft ripped them off big time. They really did. They ripped them off and came up with their first Windows operating system. Somehow in there, I don't know when it happened or who started it, but somebody got started and got in the legal business and started saying you can't copy this. And I think it was Microsoft that did it first, which really sucks because they stole it and then they said nobody can steal it. Anyhow, I'm not positive on that one. So anyway, so all this stuff saved a lot of time and energy. Now, what was taking weeks of 8-hour days, 10-hour days, 12-hour days of working on this stuff, now we were doing in a couple of hours because you could draw it on the PC, you could test it on the PC, you could put up the parameters, and it could do a lot more testing than you could ever do on the other ones. And it was all done on the PCs. Now, this thing, it is in quotes. The guy's name is Bruce Woolley. Almost every semiconductor company in the world, as well as a majority of electronic system companies, uses some version of SPICE or one of its derivatives for the design of their product. The design of virtually every integrated circuit relies on the simulation of at least some of its constituent parts at the device level, and most of these simulations have been and are being carried out using PSpice or SPICE-related programs. I thought that was important to put that out there. Almost everything you do has something to do with SPICE. So that is probably one of the most important, now my mind went blank, developments of our time was PSpice. Simplified the engineer's work a great deal. Now we're moving along, finally got into the 1980s, and we came up with HDLs, a hardware descriptor or hardware description language. I can't remember which one it is. Here I've got written hardware description language, so if I have tests and you put descriptor or you put description, either one, I'm not going to mark it wrong. I think it's hardware description language, but I know there's other places in here I've got descriptor. I did tell you the other day that VHDL was developed. The V stood for Very High Speed Integrated Circuit. And then the HDL was hardware description language again. So that was started in '81 by the U.S. Department of Defense. And I told you that the other day. A lot of companies that were out there were doing Defense Department work, and they required that everything be documented the same way. They wanted to be able to pull up and test and run anything and everything that was compatible. They didn't want to have to go, oh crap, this doesn't work, we have to change it over to something else. They were paying you money to do it. You did it in VHDL. And so that was their standard. Because of that, that's why I've stuck with VHDL in this class. This other company was developing at the same time Verilog. They're pretty much the same kind of things. These are not, and I've got in parentheses, or I'm sorry, in quotes there, they are a programming language. Well, they're not really. But they look like one. When you're typing stuff in, you're going to think, this looks pretty much like a language to me. But it is a description of how the circuit is supposed to work. And we will get into better examples than I gave the other day, but we will look at better examples that really make it clear that this is a hardware description, not a program. Okay, these designs are then used to develop ASICs, application-specific ICs. So you could, if you wanted to, develop your own little microcontroller in there, okay, that is specific for one thing, like to run a microwave oven or something like that. It take these inputs, not a whole bunch of inputs, but just this small set, so that it was specific for this particular device. Anyway, most of them were, the designs were used for conventional circuits or FPGAs or some kind of complex programmable logic device that was out there. Okay, here's a group of, this is an FPGA. It's a group of 8 logic cells up in the left-hand corner. Then a little bit bigger area, it shows a memory block. And then it shows this area where there's an interconnection wires for connecting all this stuff together. So when you're looking at that, these logic cells actually, they're more like either multiplexers or truth tables. That's all they are. The memory blocks are going to be either D or JK type flip-flops, and the interconnection wires are just, you program it and say this goes here, that goes here. But it's important to note that the logic cells are either the multiplexers or truth tables. Okay, so this HDLs that are out there allows you to describe this system using either VHDL or Verilog. How long does it take? Probably, well, it depends. If you were doing the same kind of design as what I was talking about earlier for, being a digital engineer that was taking days, if you were doing that and this, you could probably do in less than an hour. So, of course, nowadays, you can do, with the use of the computer, you can come up with much, much more complicated designs in the same amount of time as you could, let's say, 30 years ago. Then you can simulate it, and you can synthesize it. You don't compile it, you synthesize it, which means kind of make it look like it's a hardware circuit. But it's you're going to think of it as compiling, but it's not, okay? And we'll get used to the terminology as we go through it. Then you're going to download it to a development board, or you're probably just going to use it in some kind of simulator on the machine and see if it works. I think you should always run it through the simulator several times on your computer to see if it works, and then take it down to the board and make it work on the actual board. There still could be some problems there with actual timing issues or something like that. Okay, so we're going to be doing this. We're going to be using Xilinx integrated software environment. We are not using version 7.1. We're using version like 14 or 15 or something like that. The reason I started and I kept it with this, and I don't think I've made a lot of changes, is because back then a lot of the folks that worked with this software on the other side of campus, and I'm not putting them down, they had put, yeah, I am, but not really. There was only me over here doing digital and engineering technology, right? I'm the only one. There was one other guy that was doing some digital. But there was a bunch of them over there, and they had all kinds of stuff saved with 7.1. And 7.1 was had some stuff that was nice, and so they didn't want to change it. And then it finally got up to where it was like, I think it was version 13, where the changes were enough. The personnel had changed quite a bit, and they decided to upgrade it. And oh my goodness, for a lot of these guys, they were creating their own first set of slides, or they weren't even doing slides. They were just there. Y'all figure it out. I'm sitting here going, oh my God, I've got 200 slides in this 1 week of slides. I'm gonna have to take all these screenshots again. Oh, jeez. And I'm one of those kind of stupid and particular people that figure that nobody else can do it. It has to be me, because anybody else would screw it up. So I pay for that, right? I should have let somebody else do it. But actually, every time I've let somebody else do it, they have screwed it up. So anyhow, Xilinx software will allow you to describe your circuits in VHDL or Verilog. It'll allow you to draw the circuit if you want to do it that way. So you can use HDLs, or you can do circuit drawing, some kind of a schematic. And the first thing I see when something like that happens, students want to say, well, wait a minute, how many AND gates do they have on this? They don't. It's not a real chip, right? This is all simulation. There's no real chips. They don't have any real, you can't say, well, I've got 4 2-input NAND gates on this chip. There's not a chip. And you can't say this pin number 1, 2, or 3. There's no pins. These are descriptions. You might like doing the circuits. You might, and there's ways that you can do both. There's ways that you can put a circuit on there and then connect it to a hardware description, and that's kind of interesting when we do that. And we'll be doing that close to the end of the semester, where you got both of them in there and you got to connect them. Okay. So the design process, it's pretty much the same as it was before. The engineer comes up with the design. They use some kind of software, and they either use something to draw the circuit, or they use an HDL to describe it. Then they'll synthesize it, and they usually do some kind of a test on that and simulate it in some way. Then they download it to the programmable logic devices that are there to test and troubleshoot and see if it is. Often they use some kind of test bench program in there in the middle. That's what I was getting at. That lets you test it, lets you simulate it. This is a printed circuit board. We've all seen them before, right? And somewhere in there, I think I've got, is it upside down? Here's one of the FPGAs. There's one. These were Altera. This is programmable logic device. All of these are. So a lot of them out there. You can imagine how complicated that circuit is if they got that many programmable logic devices on there. And we're going to be using the Spartan 3 that has several on there. Here shows the design process. It's just a basic design loop. I'm not going to spend a whole lot of time on this. This is the guy that wrote the book that if we were using the book, this is the book we would have been using. He says it's next to impossible to be a good design engineer or a good designer without being a good troubleshooter. You got to be able to do both. Successful debugging takes planning, systematic approach, patience. You don't get to pick up the computer and throw it out the window because it's not working, even though you want to. Okay, and logic. I like this line. If you cannot discover where the problem is, then try to find out where it's not. If you can take, if it takes stuff around and go, okay, well, I know it's not here because this is all working right. You can throw off uh, large portions of the design. Another thing that a lot of students don't see is I used to work in this area too, and what I'd do is I'd go to the middle of the schematic, and that's where I'd first test and see where, how many of these signals are correct here in the middle of the board or in the middle of this design. And if they were all right, well then I just cut out the first half of that schematic, right? The problem was somewhere after that. If there were problems there, then the problem is probably somewhere up here. And I would cut it in half again and keep doing that until I finally could get in there and find out where the problems were. This is a lot of patience. It is hard to do the troubleshooting. You do have to know when to take a break. When I was working on my master's degree, I was writing a fairly complicated program for a robot using Java, and at the time I didn't know Java, so I had to learn Java, and then I had to write it for a made-up computer, a made-up robot. It didn't really exist. And because it was getting hard, I decided to make it a two-dimensional robot instead of three. I remember there was a guy in the class that had a three-dimensional robot, and he had it on the screen in three-dimensional, and he learned all this to put that up there. He was amazingly brilliant. I used to think I was smart until I met him. He was pretty smart. And actually, we had one test in this class, and this annoyed me. I don't like this, but this guy came up and said, "What did you make on that test?" I'm like, I don't like people asking me that. So,
Because he knew that he probably made a better grade.
well, and that's usually what they're doing. It's like, it was one of the hardest tests I had ever taken in my life. It was like, what did you make on this test? I said, I'm not going to tell you. I'm just not going to do it. And I got two stories with this. But finally, he bugged me so much about it. Oh, the grade I had a 44. I have never made a grade like that. And I said, okay, dude, look, leave me alone. I got a 44. He said, then you made the top grade in the class. I went, what? And I'd even beaten him. It was like, what? And even with that 44, I made an A in the class. Now, what's the idea? We're working at master's and PhD level work here. The teacher was trying to find out which of us had the stuff and could solve these kinds of problems. Okay? Now, there was another test I took here working on my BS degree, and this is when I quit telling people what I made on test. The teacher, I thought it was really mean. He walked around the room handing back tests and saying things like, I think the average on that test was about a 35. And he handed tests back and looked at people and said, well, you're a real dumbass, aren't you? And to this guy, he'd go, why did you even get out of bed today? And just some of the worst comments. I mean, they were bad. I couldn't believe them. And he looks at me and he says, and this, look, you son of a bitch, makes a 98 on it. And I went, oh my God, I can't believe you said that. So guess what happens? As soon as that class was over, we walked out the door. About 10 or 15 of those guys were going, hey dude, can you help me out? Can you help with this stuff? Now, I worked full-time and part-time, extra part-time for the money I needed to pay to go to school. And I had to be quick on my feet. What are you going to tell these guys? You going to say, hell no, go away from me, I'm not going to help you out? It doesn't work, does it? So I said, dude, look, all of them. I said, just look. I work full time. I do extra stuff part time. Now, if you want me to help you, I'm going to have to quit that part time job, and I'll have to charge you $25 an hour to help you. They were like, you're kidding. I said, no, I'm not. And they thought I was an ass, and so they left me alone. Just exactly what I wanted. Everything worked out. I didn't care if they thought I was an ass. That was fine. I just wanted them to leave me alone. When I was working on that program, back to that story, there was about 5 stories in there. My wife would come up to me when I was working on my master's, and she would take the laptop away from me. I'd be going, what are you doing? Leave it alone. No, no, no. Get up. Back then, I smoked, and she hated it. She'd go smoke. Go have about 10. Go sit down somewhere and smoke for a while. Go for a walk. Get out of here. Have a drink. Here's a beer.
That is an awesome life.
And it's like, just go do all this stuff. And it's like, because she knew I was just about to toss that laptop out of the room, out of the house. Whoosh, just throw it away. So I wasn't seeing that my patience was about gone, but she did. And she made sure I didn't kill everything. Okay. Again, here you see it a second time in troubleshooting. Break the problem down into smaller problems. Always. That's that is one of the most important things you're going to hear. And I already said this too. Look at just parts of the circuit to see if that's working right here and there, and be able to wipe out whole sections of your design to see if it's working. Be systematic in your approach. Before an IC is replaced, I don't know how many times I saw people take ICs out and bend up the pins and throw them away, and it was a good IC. And what would happen would be that it wasn't that IC's fault. It was the next one down the line that was pulling this one's output low. So it had some input problem where it was shorting out to ground. And so if all they had to do was desolder this one output pin and make sure it wasn't connected to anything and then test it, and if it was doing good, it wasn't this chip. It was maybe the next one down the line or another couple down the line. But there was a lot of folks I could not make them see that, and they'd be throwing a lot of good chips away. So make sure that thing really is at fault before you get rid of it. Anyway, what else have we got? Another useful tip. This was I think the one for going halfway. Yeah, this is one just looking at a halfway point and seeing what's working and what's not. This sucks. This is something we don't think of.
That's the worst case.
There could be more than one problem, right? You always think, oh, there's one. Well, there might be 4, and you're thinking there's one. And God, it's going to take a while to figure out something like that. Again, you have to start breaking it into smaller problems to be able to do this. And like I said earlier, or that other guy, Wakerly, said earlier, to be a good design engineer, you got to be a good troubleshooter, because you got to be able to figure out how to do this. Okay, so you look at small parts of the circuit first. Break it down into those smaller pieces, and hopefully get rid of whole functional blocks of a schematic, so that you can see if it's gonna, if you can get rid of half of this thing or more. Here, what level are you going to be designing at? I don't know. I don't know. I've got students that have graduated and they're working at the computer level. Computer's not working, they swap out computers.
There we go.
Yep, that fixed the problem. We've got people in there or that have gone out there, and I'm not saying anything about their level. I mean, they took jobs based on, was there a job available? Did it pay well enough? Was it in the area they wanted to be? La da 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 da, right? I knew one guy really good, and he would not leave this area for anything in the world. And I kept, he was one of our best students. It's like, dude, if you're not willing to move away for a little bit, you're really cutting your options down. I knew that because my wife wouldn't let me move, so I got stuck here. That sounds bad, doesn't it?
That does sound a little bad. A little bit. Not
I'm kidding. I'm kidding. I've enjoyed really working with the students mostly for all the time I've been here. I've been here something like 13 years, and I've enjoyed it working with the students. I've only had one or two times where I had a group. There was one group. Remember the one I told you about that I turned in about 10 of them for cheating? That was like a third of the class. That group individually, there were some nice folks. As a group, they sucked. I didn't like them at all. And I'd come into the class and it's like, damn, I got to teach you guys again. So anyway, you might work at the board level where, you're opening up that computer, but you got to figure out, is it the power supply or the motherboard or one of the other boards? That's a whole different ball game, right? And you have to figure that out. Which one is it? Of course, you might get down to the ICs on some of those boards. Now, to me, it's starting to get more interesting. You might actually start looking at some of the circuits on the chip and which one of these chips is good or bad, right? And then you might get down to where you're actually working on this level where you're looking at the gates themselves. I doubt you are going to be working down here. This would be where you're actually, instead of the transistor circuits, you're actually working on the ICs themselves. I know of one guy that we've had in almost all this time that I've been here that is working at that level, and he loves it. But he's not, I don't think he's getting paid enough. Okay, professionalism. I know you guys hate documentation. You think it's one of the worst things in the world. You have got to document. Another one of our most successful students. In fact, he was at I don't know if I was telling you or a different class. We're at a party a couple weeks ago, and he was there. And he is really one of the best engineers at this company. Okay, and he two things he didn't like to document. And the other thing that we used to tell him about all the time is even in email, he would have a misspelled word. And we would say, you cannot do that. And he would do it anyway. So the first thing that happened at this job, I don't think he had been there 3 weeks. They said, if you can't learn to spell, you're out of here. We don't want to see one more spelling error anywhere. And he was like, holy shit, this guy was one of the worst spellers I've ever seen in my life. I mean, he might have spelled cat, K-A-T, and think it was right. Okay, so he had to buckle down and really, and he was also one of those that really believed everything he thought. So if the software said K-A-T is not right, he'd say, yes, it is, and put it in his dictionary. So he had to go in and get rid of all of his dictionary stuff and relearn all this. and it took him a little while longer to do stuff, but he would go through, I think he even bought some software to help, like he was a little kid, learn how to spell. And he hated documentation, but about half of his job was documentation, and they do require it. And so you've got to get used to it. And just, let's say you're making 50, 60,000 a year. Just think of it in terms of, man, they're paying me this much to write this down on a piece of paper. My wife, bless her heart, she is a wonderful, wonderful woman. She has put up with me for 25 years. I know she deserves a medal or some kind of. Actually, one year I gave my father-in-law a trophy because he put up with my mother-in-law. She is an old bag, let me tell you. Now, but okay, wait a minute. Now I forgot what I was going to say. She she was working in a school system as a counselor, and I would agree with her. Like everybody else, they do not treat teachers or counselors or any of those people right. They just don't treat them right. But she made good money. She, made, gosh, I don't remember, but it was like 35 or something like that to be a counselor. That's pretty damn good. And she was so angry that she had an advanced master's degree. I kept telling her, you got to get over that. Big deal. I got a PhD. It's nothing. Don't worry. It ain't nothing. They don't care. But they would make her go out in the mornings and open doors to take these snotty-nosed little brats and help them get out of the car. And she would have a fit. I said, they're paying you $35,000 to open a damn car door. I'd do it all day long. That worked for about a week. And then she didn't like it again. And I was like, oh, come on. But she was right. That was the wrong use. She should have been doing something a little higher level than that. But still, do what the companies ask you to do. Learn to love it. If you don't like it, go somewhere else. Otherwise, you're making yourself miserable and them, and nobody's having a good time. So get rid of it or get out of there. You are going to have a career position when you get out of here. It is a career level position. You may have a title. Some of the guys coming out of here are called engineers. They're not really. They might be called technologists. They might be called programmers. They might be called designers. Whatever that is, whatever title they give you, they're paying you a pretty good salary, and you're a professional, so act like it. Okay, so that means you're going to have to communicate with other people. Some of them are going to have lower degrees, some are going to have higher degrees, and some of them are going to be your managers, some are going to be customers. The better you can do this communication, both in writing and verbally, honestly, the higher you'll go in that company. That's all there is to it. The better you are, the better you are at doing that stuff, the higher you'll go. If you can actually play the game and not be Sheldon, let's put it that way, and not be Howard. If you can be a pretty nice guy and smile at people, and even if they're stupid, say, well, that's not exactly the way I would look at it. I would think it's more like, then you'll be out there working with customers and you'll be making the higher amount of money. So it's worth it. Okay? So the goal of this course, students should be, this is what it says on the syllabus, you should be able to design, test, troubleshoot, and implement combinational and sequential digital circuits in a professional manner and by using medium scale integration and programmable logic devices. Okay, so we've got a pretty tight time frame to do all this stuff. So we're going to move right along. Somewhere in this class or the lab you're going to be doing a lot of writing. You're not going to do as much writing as in here, but when we get to the projects, you will be doing some writing. I expect professionalism. Okay, you have to do it. It'll be a part of it. How does it look? Do you have misspelled words? Did you follow all the rules for doing this? And somewhere, either here or the lab, somewhere, we're going to have some kind of oral assignment. So you have to come up here and give a presentation to the class. How many of y'all like that? You get nervous doing it? You're not.
I don't care. I can do it.
Yeah, there are so many people that don't like it. In fact, before I started teaching, I would be like this in front of the room. In fact, this one I thought was kind of funny. I got this thing. These things didn't exist, a long time ago. And I was standing there like this in front of a class. And I had been teaching for years, but here I'm like this, scared to death, and I'm giving this presentation. Well, it wasn't I hadn't practiced enough, right? So I'm like this. And I finally put my hands behind my back because then nobody could tell I was shaking. I gave my presentation. I was hitting the buttons. And at the end of it, it was like, oh, God, that was the worst presentation I've ever given. And I asked somebody after class, I said, dude, how bad was it? He said, you were fantastic. I couldn't believe how good you were. And you had everything timed perfectly. He didn't know I had one of these. He thought I just had it running. Most of the class thought I just had it running, and that I had that thing down so pat that it was just moving on its own. Anyway, anyhow, that's it. 77 slides we got through in that amount of time. So, isn't that what it says?
29.
29? There was more than 29. It says 29. That's a bunch of poop. I was sure there were 77. There were 29. Yeah.
Were you able to figure out the food spice issue that we had in the lab last Friday?
I can't remember what the issue was.
It was like you needed to go find libraries to be able to use certain like vets or whatever.
No, they're there. What I have to do is sit down with you, and we'll find it. We'll go find
So we'll do
it.
that on Friday, I guess.
I'm sorry?
So we'll do that on Friday or something?
We can do it before then if you want.
Okay.
Now, I won't be around much tomorrow. Let me turn the...
When are your office hours?
Let's see. When are my office hours? Let me turn the recording off here. Okay, bye, DE guys. That's it. Hope it worked.